So that was a two-way ANOVA. You can actually have ANOVA with even more effects. So for example, if the first example we looked at, where we were looking at the effect of strains of mice and the injection that was given to them, if those mice had been in different cages, you could allow for that in the same model, which would probably make the model more efficient, and that would then be called a three-way ANOVA. And so you can actually put as many effects as you like into the ANOVA model. And of course, yeah, you could have the interaction along with that too. So a model, we've got three effects here, three effects and an interaction in this model. You can have even more, but it's important to remember that things fitted in the model in ANOVA are always categorical. The strain, injection, cage, these are all categories, they're groupings of data. So that's what ANOVA is used for. The last thing to say about ANOVA is that we looked at the paired t-test last time, and it's just to sort of show how it all fits together, to say that a two-way ANOVA can give you exactly the same results as a paired t-test. So it's taking into account the association between two measurements. This was the example we had last time, where there were 8 animals that had a measurement taken before treatment and after treatment. I said you could do a paired t-test to work with these animal differences, but an alternative way of analysing that would be simply to do a two-way ANOVA model and to fit the animal effects as a factor in the model. So the next slides have got the output from the two analyses. So this is the output we had last time. The paired t-test gave us a significant p-value. And the main thing to note here, that if you do the ANOVA and fit this model with animal fitted in the model, you get exactly the same p-value. It results from what's called an f-test rather than a t-test, but in this case the two tests are equivalent. This f-value is going to be the square of the t-value, which should be given t-value there. It's the square of 2.23, 4.96, and it'll give the same p-value. So you don't need to worry really about the equivalence between f and t, but the main thing is you get exactly the same p-value from an analysis of variance with this kind of format as you would if you did a paired t-test. So it's quite nice to know that, although in practice, if you just got two sets of data that were grouped, then you probably would just do a paired t-test. If you had 3, that's where ANOVA came in. If you had several measurements, then you can't do a paired t-test because you've got too many measurements, but you could still fit an analysis of variance model.